Hello and welcome back to Calculus 2. This is section 6.3, disk and washer method, also known in the book, I believe, as volumes by slicing or whatever they have. We are going to take a look at using integral to compute the volume of objects that have radial symmetry. Radial symmetry meaning if you cut them in a particular way, they will have a circle. So we are talking about pipes, light bulb, baseball bat, those cups you guys have, bottles of water, and whatever else you have here. Your mug over there, excluding the handle, this spray bottle over here. Anything that you can obtain by rotating a function around an axis to create a three-dimensional object. So if I take this line like this and rotate around x-axis, I am going to get this line on the other side as well. It will create a circle like this, and you get a cone. So if I rotate over here, y equal mx plus b, some linear line, well, actually it's just mx because plus b is 0, right? It goes through the origin. If I rotate some kind of y equals mx, I'm going to get a cone, right, as a three-dimensional shape. So we have a two-dimensional graph, and then you draw the line, and you rotate that line around x-axis. You can rotate around y as well, and it creates a three-dimensional shape. Now, the feature is that it will have a circle when you cut it like this, right? Anytime you cut perpendicular to the axis of rotation, you will get a circle as a cross section. And that's why we call it a disk, right? Because you know what the CDs are, right? They're still around. So a CD is a CD disk. It's a circle object that's very, 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 very thin. Now that very, 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 very thin is going to be our dx deal for the integral that it's coming up. So when you take a stack of CDs and you put them all on top of each other, what you get is a cylinder, right? You get like, it's like a tube. But you can take each individual disk and hold it in your hand, and it's very, very thin. So that's the idea of this, that we are going to have infinitely many, infinitely thin disks stacked together. And they actually don't poke out of the object. They are exactly the width of the object. I don't know why I did that. So these disks would be as wide as the object is, and they're not all the same length, obviously, same size, same area, because as we go from left to right, the object gets fatter. Now, here is another example, and I would like you to tell me what would this one make. So I'm going to rotate this time around y-axis, and I'm going to have a line segment offset. For instance, let's say here. So what would I have in this case if I rotate around y-axis? Yeah, so what do we get?
It'll look like a truncated cone. The cone is kind of missing its point.
Truncated cone is correct. Can we go with the shape of an object that we actually get? You're rotating.
A donut.
Nope.
I feel like it's the same thing with just vertical.
Well, it would be the same thing if we went from the origin, in which case it will create, right? Okay. I shifted it, so what is it?
Oh, it's not in the shape, it's not close.
Well, it will be when you start rotating, you will get the other one on the other side. You put the two circles on top and the bottom, and what do you get?
Is it just a cone with an open head?
Yes, it is. But what is it?
I mean, like, I'm picturing like a soccer cone, like this ball with an open head.
An irregular cylinder.
Nope. You see, you guys are just going math. Just get out, snap out of math. What do you get when you rotate that line around the y-axis? Coffee cup, finally, thank you. Can you please model that for everyone in the classroom? There you go, look at that. You get that object, right? There's another one, pink one in the back, right? These are, see, when you put the same line in a mirror image on the other side, and you put these two circles, right? You get a coffee cup. So one of your possible project problems might be to go to your store or cafeteria here or anywhere else, pick up the cup, and then do the measurements so that you can figure out what the y equal mx plus b is over here, and then use the formula we're going to learn now to calculate the volume of the cup. Then convert from, whether you do in centimeters or inches, convert from centimeters cubed or inches cubed into the fluid ounces, and figure out whether the cup advertises proper volume inside, right? Because if it's not, you don't have to go to school anymore. You're done. All right. So this is something. Okay, let's go with this. Rotate on x-axis. What do we get?
Egg.
No, eggs don't have the spiky ends.
Football.
Football. Yes. See, even I know.
Baseball.
Baseball bat, exactly, right? So you can create a whole bunch of objects just by figuring out what kind of a function would rotate around. So now I'm going to take this spray bottle, make the epic journey all the way to that other board over there, and just trace the bottle onto the. So without the spray top, I'm just going to trace the bottle here, and then okay. So this is the trace of the bottle on the board. If I draw the y-axis, in the middle over here, I draw the x-axis, and I send this rotating around. If I am able to figure out the formula for this function here, f of x, I can quickly compute the volume of the bottle. Then you can pour the liquid inside the bottle, pour the liquid from the bottle into a measuring cup, and you can verify the volume, and you would have the calculation, right? So, and they should be close. Obviously not going to be the same because there's always error in measurement. Now, my favorite overachievers would actually go to chemistry lab because they have those very precise graduated cylinders where you can measure the liquid. Especially in my Calc 3 class, because one of the project problems for Calculus 3 in my class is to calculate the volume of an egg, right? In which case you would have to model the egg. An egg models as a paraboloid on one side, and then the bottom is half a ball, right? Half of a sphere. You glue those two objects together, you get an egg. So we have formulas that compute volume in Calculus 3 for shapes like that. And then the students, obviously the step number one, boil the egg. That's the first step, because you're going to move the egg around a lot. So once you trace the egg on a square paper and do all of those things, as I said, my favorite overachievers, right? They take the egg to the lab and they submerge the egg into the water to take a look at the difference of volume, right? Because the water displacement will tell you the volume. So you can do that in a bathtub with the water level. If you want to know your volume, right? You know your height, you know your weight, you know your age, right? Do you know your volume? No? There it is. You can do that. So so you can calculate the volume using graduated cylinder. So you read along the line. Many students found that those kitchen measuring cups are in some cases terrible in terms of they're really off. We're talking like 10% off, which is insane. But that's, goes on a production line and just, slaps the print on it, going fast to make as many as possible. So if something goes out on alignment, the print goes up or down. So, those are not very reliable. Now, obviously, the ones that are in the chemistry lab are. So there's that part. Anyway, so now going back to looking at these shapes, you draw a shape of some sort, and then you rotate on one of the axes. And when you rotate on one of the axes, you will create a three-dimensional shape, and that shape has to have a radial symmetry, has to have circle on one of the sides. So as you're looking at the bottle, you do not see any circles, you just see the bottle. It's like a rectangle, and then this is not a triangle, but let's say a triangle, right, when you look at it. But when you flip it this way, there's the circle. Anywhere you cut along perpendicular to axis of rotation, anywhere you cut perpendicular to axis of rotation, you are going to get disks, which is why this is called the disk method. Now we're going to take a look at the formula which you are memorizing to calculate volume for the shapes that are obtained by rotating a function around an axis. We start with the volume for rotation around x. So I'm just going to put x in this little arrow that rotates around it. So volume is equal to pi integral a to b of f of x squared dx. So this is your disk method. For rotation around x. And immediately I am going to write the rotation around y. So here's the blue companion from, so pi c to d, because these are now y limits, of f of y squared dy. So these two formulas together, it's the same formula. One is in the x direction, the other one is in the y. So I need over here y with the arrow around it, signifying that we are rotating around y-axis. So this is what we have for our disk method. Now, why is this formula it? Obviously, some of you would rather know the concept than memorize the formula. See, we said that when you cut the object, let's say you have the object, it's a cylinder, and there is the axis of rotation is x. When you cut the object, you will cut, let's say here, this object would be a very thin disk. Thin disk. And if you take a look at this very thin disk, this disk has the area over here and has delta x as a height, right? Because this was delta x cut over here on the You took a little tiny slice. When you go to bread place, they say, would you like the bread sliced? Then they give you the dx slices. Just terrible. So you have this disk, and what is its volume? Volume is going to be area of the disk times delta x, which is the height of the disk. Area is pi r squared, and we know that dx is equal to dx, delta x is equal to dx from calculus 1. And that's exactly the formula you have. See, this is just one. And then you involve adding infinitely many of them. So I hope you see, if you look now at the screen, you see pi r squared times dx for the height. Right? It's exactly what we have. Pi r squared. Now, why is f of x r squared? Because the radius pokes from the axis of rotation up to the function f of x. So if you have, let's say, I draw that cone, right? And you have your axis of rotation here. You see that this is your f of x function. Radius is this, and then radius is that, and radius here, and radius here, right? Radius is always from axis of rotation poking towards the function, all the way to the function. So function is the radius for for our circle calculation. So that's why the formula looks what it looks like. It's simply area of the circle times the thickness of the object. Now dx, that's very thin, but integral over here gives us infinitely many of those stacked together. I asked you to think of those stacks of CDs. You can buy a bundle of 50 or bundle of 100 on that stick, right? So, well, not anymore, but you used to 10 years ago. So now we know what the formula is. And with this, we can go and we can calculate volume of different objects as long as you are able to integrate using Calc 1, right? So let's say that you want to calculate, well, let's put something over here. Something that we can easily check, which would be a cylinder, a tube. So let's say you have a straight line segment going from 0 to 1, 2, 3, 4, 5, 6 to 7. We rotate this on x-axis, which would put the line on the bottom as well and create, you know what, I'm going to go with a dashed line and dashed circles over here. So we know that our f of x is just equal to 2, because that's the y equals 2 line. And you are rotating that between 0 and 7. So volume for this would be pi 0 to 7. You're integrating 2 squared because your function is 2, the radius is always 2, dx. And that should be something that you can integrate, hopefully, very quickly. What do you get? So we are integrating pi, we integrate 4 dx from 0 to 7. So you get 4x, so pi 4x from 0 to 7, and you should get 28 pi, right? Now, the reason why I went with this joke of an example is because we can calculate the same volume without calculus. We know the formula for cylinder from our middle school or whatever. You learn that the volume is area of the base times the height. If your height is 0 to 7, right, if you stand this object up, so h is equal to 7. You know that the radius is 2, so r equals to 2. And then you just plug in that the volume is r squared times pi. There we go. Pi r squared times h. So that's pi 2 squared times 7, which gives us 28 pi as our volume. So that was a very simple example, just to see the formula at work, very basic. Now let's say you decided to make the money by tutoring math because you can, and you are tutoring this little kid in middle school who's having trouble with these volumes. And you teach a kid a formula for the cone, right? The volume of the cone, which is 1/3 pi r squared h. That's something, again, you learn there. And the little kid goes, why? Say no more. Let's go. Here is why. You immediately draw x and y coordinate system. You set up the integral, and there you go. See? So you set up this. You know that it will stretch r units out, and it would be h units high when you have the integral. So now we need this formula here because it will rotate around y-axis. So we need to figure out what is this y mx plus b so that we can calculate the rest, right? So what we see is that the slope m is height divided by radius, and it's negative because it drops down. So negative h over r x plus, and the y-intercept is h. So that's our function for in terms of these. Now, obviously, if you have numbers like 2 and 7 from last example, let's say, then you would plug in 2 and 7, not r and h. What we are doing now is we are doing mathematical proof for the formula that gives us volume of the cone. That's what we are working on right now. Now, since we are rotating around y-axis, so that's a y-axis rotation, we need the dy integral. And if you have a dy integral, you must have f of y, not f of x, which means you need to flip this formula to get what you actually need. So flip, you will get y minus h equals negative h over rx, and then multiply both sides by negative r over h so that you can get x by itself. So negative r over h times y minus h is equal to x. So x equals, remember, when you need f of y, it's x equals f of y, which is why we are solving for x. You can't do that all the time. Sometimes you can, sometimes you can't. So in this case, we can, so we're going with it. So now this is going to be negative r over h y. Negative and negative give me positive. H and h cancels, so it's just r. So we flip the formula, and now I have my x equals, which is actually f of y, equals negative r over h y plus r. this skill is important because you need to sometimes switch from one side to the other. So make sure that, basic algebra works for you. So now we are going to move to the integral, right? This kid is still observing what you're doing because you are explaining why. V equals pi integral, and now your limits are 0 to h because you are using y limits because it's your dy integral. This is something that you guys might not be good with yet. Make sure that if you have your f of x dx, you have your x1 and x2 limits. If you have your f of y dy, make sure that you have your y1 and y2 limits. It has to be x across the board and y across the board. We mix them in Calc 3, but they're still separated with some features. So x limits with dx, y limits with dy. So since I have y rotation, I have dy. Since I have dy, I have to have f of y. And if I have f of y, I better have y1 and y2 limits. That's the process of, maybe I should box this so you can quickly see. So everything started with a y rotation. Y rotation says it's a dy integral. And then if it's a dy integral, the other variables have to match. Now look, dy is telling us we have to use f of y, and f of y told us that we have to switch all of this. And then, because we have f of y and the y, then those are the y limits, which means I will read 0 and h as my limits for this problem. So now I have pi 0 to h. I have the function that needs to be squared. Oh, kill me now. We gotta square this thing. Negative r over h y plus r squared dy. So this is the integral that we have to solve. And when we are done, now r and h are parameters, are numbers. So those would be, 3 and 7 or whatever. So don't panic about that. The reason why we have them as r and h, because we are shooting to end up with this formula here. That's what we are aiming to get. So now let's go. Work this out. We have to square the binomial in here. We have two terms. So when you square the one on the left, it becomes r squared over h squared y squared, because each one of them picks up a square. Then you have the middle term, which is 2ab. So that's going to be negative. And when I multiply r and r, I get squared. So negative 2r squared over hy, and then plus r squared. So that's our squaring right there. The middle term is usually the one that creates noise. Again, it's 2ab. This is your a, this is your b. So a times b, well, r times r is r squared. And then you have a 2 for 2ab. Maybe, let me just write this in blood just in case. So 2ab over here, so there you go. All right, so now we are integrating because that's the next step. R squared over h squared, that's a constant, right? Remember, r is going to be 3, let's say, and h is 7. So you're just having 9 over 49 there. It's a constant, just move it. It's y cubed over 3. That's the integral piece, because your integral integrates y. So y is the variable. You're integrating y squared, so you're getting y cubed over 3. Now minus, again, this mess over here is constant, so you copy that, and you get your y squared over 2, plus copy constant, you pick up a y, and limits are 0 to h to get this thing. So now we, well, first we can cancel these 2's over here, right? And now we plug in age. Now when we plug in 0 for y, it's just going to kill all the terms, so we don't have to worry about 0. We just plug in age for every y. Don't forget pi in front. So we have r squared over age squared. Age cubed over 3 minus r squared over age, and here's your age squared now because it's your y squared. You plug in age, it becomes age squared, plus r squared age minus 0, 0, 0, no one cares, right? So now we have pi, cancel what you can. Age squared will kill the cube, and you just have age over there. The square kills the age over here, and that's it. So what do we have? We have r squared age over 3 minus r squared age plus r squared age. Well, these guys are exactly the same, so they just drop, right? That's like negative 5 plus 5. So they drop, and there you have it. 1/3 pi r squared age. It's a formula for the volume of the cone. 1/3 pi r squared h. Yeah, it's a conversation starter, definitely. It's
A little kid
On your-
gets it now.
yes.
Now it's very clear.
I mean, come on. The tutoring generates a lot of money, right? There's no job that you can do now that can match that, right? Think about it. When
And
it's
it's per hour, so if you show them this, you make extra money.
see. Also, this is a good thing when someone says, what's new? Work this out. You're out at a dinner, write that on a napkin, leave it behind, see if it's going to cause any, wow, what is this? Wow. Or another good Thanksgiving dinner. Let's say you don't want to go, but they're making you go. Just 1 year of this. Guaranteed you can stay home, play games. They'll bring you scraps. Trust me, they love you, all right? They'll bring you scraps. You can play video games in peace, all right? You know, from experience, all right?
I just have a question about this. So like, are we thinking in terms of like 3 dimensions?
Yes, this is a third dimension because, right, you get to touch the object.
Right.
This is the ice cream cone, right? You hold it in your hand. 2-dimensional objects are the pictures on the board.
Okay.
You never get to play with 2-dimensional object because 2-dimensional object is just this black outline or whatever color you use, pen, on the piece of paper or a board or a wall, right? 3-dimensional objects are the objects that you get to hold in your hand. So this is the only excursion that we are going to have in a 3rd dimension in Calc 2.
Okay.
We are going to deal with volume and the surface area in, I believe, 6.6 or 6.6. And so we have 3 lectures in Calc 2 that are dealing with volume, which is 3D. Everything else is going to be strictly single integrals and areas and stuff like that. So the first 4 chapters, right? This is first out of 3 lectures on 3D stuff. Now your Calc 3 entire course is 3D, right? That's what really shines.
So it like can you think of it as like X and Y or the coordinates for like 1 dimension, and then R and H are the coordinates for the third dimension? When
Okay, so we'll have to discuss that. First, we're going to agree that x is its own dimension and y is its own dimension. Now that you're, well, this is the worst possible classroom in the whole college for me to explain this, because it's not a box. See, this is octagon over here. It has 8 walls. Terrible. Look at your desks. They're boxes, okay? Your desks on a surface is your xy plane. I can also call this board xy plane. But then there is the height of the desk, and that's z. So this desk is a three-dimensional desk because you have x, and you have y, and then you have z, right? So 3 axes. And each one of those lines, which we call coordinate axis, it becomes 1 dimension. Now, when we deal with our area under the curve, the integral, right? The function, the spacing between the x-axis and the function gives you 1 dimension of height, which is f of x. The width of the delta x, or from a to b, gives you the width. So the width times the height gives you the area under the curve. Now, for what we do here, you have a circle, and that's your f squared. F squared is 2 dimensions in it, because you have f times itself f. So f times f squared, that's 2 dimensions. And then you have a third dimension is dx, which is the height that stacks. So from a to b, dx is a third dimension. So that's why these integrals are three-dimensional. The other way I can explain that is to show you the square, and the square has a and a as their length and width, and the area of the square becomes a squared. That's still 2D, it's area, but you only have a in it. You don't have a and b. You have a and a. So now for the circle, which is corresponds to a square, you have a radius this way and a radius that way. So area is pi radius squared. Circle, do you see that actually circle is a square times pi to round the square off?
Oh my God, stop it.
I can't, this is my job. So same thing I say when someone says, oh, get out, I can't. See that? Because you have the, right? So it fits in a square. Circle fits in a square. So the formula is the same minus the pi. Pi is the one that rounds it. Now, if you take a look at their more general object, the more general object would be a rectangle over here that has A and B, whose area is AB. But the more general object for a circle is ellipse that has radius A and the radius minor radius B right there, and its area is pi AB. So those are the 4 shapes that click that way, where these guys over here are just special cases when A is equal to B. So we gave them the special names. These are the boss shapes. These are the boss shapes. So, and these are the special case of these boss shapes, right? So if you see A and A, yes, it's the same letter, but it's still 2 dimensions there, because you have A in X direction and A in Y direction, so it's 2 dimensions. So in our formula, when I write our formula for volume here, pi integral f squared dx from A to B, this one brings me 2 dimensions, this one brings me 1 dimension, for a total of 3 dimensions. And we do calculate volume in this case, because we have, right? So that's the way it works. It's really cool.
Question.
Yes?
So for the first 2 examples, the square and the circle, what if your A is 2? Then the area of the square is 4, but what if the area of the circle be more?
It is. because I didn't say they're the same. I said they have the same r square a square feature.
Right.
The other one is times pi to round it off. So observe that when you put this in a box around, which is a square, if your a is, let's say, a 2, then in this case r is 1 to have the same width, if you want the same width, right? Because radius is half of the length.
Okay, I was thinking diameter.
So yeah. So, well, diameter would be 2, in which case, right, the radius would be 1, and up there you would have 4,
Right.
and down there you would have 3.14, right? Because radius is 1 square is 1, times pi is 3.14. So you have that, right, about 0.86, which are these corners that you don't have when you do the circle, right? So that's the cool feature. It has to fit, it's math. Otherwise we go home. And everything we ever built falls apart. No, I'm serious. I mean, everything is based on this. So if you don't get to change it. That's the trick. All right. So what I would like to do is I would like to take a look at some of the homework problems, guys. This is you learn the formula of pi integral f of x dx, f of x squared dx, and you just figure out which way you have the things go. So let's take a look at some of the homework. My access to the new edition of the book expired. I sent an email to renew. So I'm going to use the second edition book, which is, so the numbers are not going to match. So I'm not going to put which problem number I am using, because it's not our edition. So I'm just going to, and you will be able to match the picture to the picture in the new edition. Now, if you do have a blue book, which is it will match the number. So let me just get in here. So what I'm doing right now is, see that, the blue one? That's the second edition. Your book is third edition, it's green. So if you are using old edition of the book, then the problem that I do now as an example will match 100% to it. And they actually have them, but they are at a different location because they added extra problems for the third edition. Third edition is supposed to have about 17% more problems than the second edition. So, we're just gonna jump in here. Drops us in chapter 14 for Calc 3. Yeah, what are you gonna do? Let's go. The chapters are different. That's a biggest issue between blue and green book, guys. If you are using the blue book, you will have to make sure that you are matching the chapters, because chapter 6, and then you chop off the last 3 sections of chapter 6, and they call that chapter 7 in the new book. And then chapter 7 is actually chapter 8, and the last section of chapter 7 becomes the new chapter 9 for the new book, and so on. So it's a journey to get all of these sections to match. Okay, volumes by slicing. Actually, I'm going to jump here and then go back. It's faster. And as you can see over here, you have a lot of these cool exercises to practice. And I'm just going to work out on 19 here, which has this exponential function. And so we did the cone already. They have the cone that goes from 1 and 2, right? Radius and height. We did that in general terms. And now let's just take a look at this one. Now this is problem 19, but it's not going to match your addition, so I'm not going to write it. E to the negative x. And they are rotating like this. There's a radius r. from 0 to ln 4. What do you mean you can't see? It's right there.
It's getting written on the live stream.
Yeah, but it's right here. Why? Oh, you want my ugly drawing? By all means, here you go. I didn't know you liked that so much. There you go. See? Now, this is a straightforward problem, guys. Plug in the values into the formula and just plow through calculations.
anyone get an answer?
A negative answer.
I got 2.
I got,
No, I got 2 answers.
oh, 2 answers? I got negative 64 plus pi. Negative 64 pi plus pi. Which doesn't make
I
sense.
think that's gonna be right.
What's
What?
it?
The y-intercept would be 1. So it would be something between like 1 and 2.
I got what's the integral of e to the negative 2?
Negative 2e.
Isn't it e to the negative 2x over negative 2?
Over negative 2.
Oh, wait, no. I thought e was,
Yeah, I didn't use it.
That's what I did too.
Just go away, but yeah, it's used up, so I got e over negative e over 2 to the negative 2x.
wait, when you're integrating, I thought e stayed the same throughout everything. It was always whatever its exponent is. Like,
Yep. You can memorize the formula or use U sub. Either way, whatever makes you happy, right? It's calculus. Your happiness is our primary concern. It's like
I'm so glad to hear that.
like United Airlines. Just don't cross the line. All right. So we are rotating on X. See, this is where I start every problem. I say, but it happens in my head. I'm going to write it for you, obviously. If it rotates around X, we are using dx, right? Which means f of x and everything else. The formulas are given at the beginning of the lecture. We have rotation on x in red and rotation on y in blue. By the way, you can follow the lecture as it goes live, and then you can scroll back if you missed something, right? Let's say you're not taking notes. You're late or whatever. If you boot the computer in a desk and put up the stream is about 15-20 seconds delay. You can always go all the way back to the front of the video to find either a formula or a concept or something. So, all right, so here we go. We need x limits because we have dx, so 0 to ln 4. We have our function squared dx. And now, Calc 2 is over. I mean, for this lecture. Now, Calc 1 takes over. Do you know to integrate this, right? So Calculus 2 is you memorizing the formula, the concept. That's it. The rest is Calc 1. So now we have integral of e to the negative 2x dx from 0 to ln 4. The integral of this one is e to the negative 2x divided by negative 2 from 0 to ln 4. Now, you either memorized the formula of e to the ax over a, and our a is negative 2. You either memorized that, or you are doing the u sub. Right? So one or the other. But either is in Calc 1. So once we integrate, we plug the numbers. We have e. Well, I'm going to kick out negative 2, put it on a pi, because it's going to be there for both of these. This time we have to plug in 0. What's e to the 0? 1, right? So we can't ignore it. So we have e to the negative 2 ln 4 minus e to the 0, which is going to be 1. This is negative pi over 2. Okay, now we need to deal with this e to the negative 2 ln 4. Negative 2 jumps inside ln 4 as the exponent of 4, and then it becomes 1 over 4 squared, which is 1 over 16. So this is e to the ln 1 over 16. If you forgot the rule from pre-calculus, from like 10 years ago, here it is. Ln x to the p is p ln x. That's the rule of logs. And that negative 2 is p in this case. So it goes as the exponent of x. Your x is 4. So you have 4 to the negative 2. Now negative exponent pushes everything down in the denominator. So it's 1 over 4 squared. 4 squared is 16, so 1 over 16. Minus 1, e to the 0 is 1. Negative pi over 2. And now ln of 16, e and ln cancel, so you get 1 over 16 minus 1. Guys, your volume should not be negative, right? But look, 1 over 16 is smaller than 1, so when you subtract it, you'll get the negative, and it's going to kill the negative in front of pi over 2. So we are good. So this becomes negative pi over 2, negative 15 over 16, for the total of 15 pi over 32 units cubed. If this was in inches, inches cubed, centimeters cubed, whatever the measurements were, right, the units. And that was the object. So now for the second part of the same lecture, we have to understand that what we calculated so far were solid objects. You cannot stuff anything inside because the entire object was just a solid block of plastic, metal, wood, whatever, right? Like a baseball bat made out of wood. It's not hollow inside. I think the metal ones are hollow inside, right? Otherwise, they will be
Practice bats.
Yeah. So let's say that you actually want to have an object that has a hole inside, a holy object, like this one. So this object, if you look from the outside, it's a cylinder, right? And we know that if you just, have y equals to, 2, and rotate that, you will get this object. But look, if you have a first radius to be 1 and the second radius to be 2, then the material is in between 1 and 2. And over here stays the hole and nothing outside. So we have another formula, which we call the washer method, which is the upgrade to this. And that formula allows us to create objects that will have a hole, which means that you can create objects that, right, they're solid, but then you can use them as storage, like a cereal bowl or something like that. So now the second part of this is the washer method. And that involves two functions. Just like area between two curves, now you have two functions. So let's say you have some kind of a parabola for f of x, and then maybe a linear line over here for g of x. And you rotate that around x-axis. So now, if you draw the other side, it's going to look like Pac-Man. It will still have, right, the circle over here. And this would probably be the weirdest cereal bowl you've ever seen. Because on the outside, it will have the shape of a cereal bowl, right? It will be wobbly because we did not make it flat over here, so it would wobble around, which obviously brings more fun times trying to chase the cereal around the milk as you eat. But look at the inside. The inside is a cone. So that's also weird, right? Because you will never be able to wash out milk out of this point here, right? It's always going to be there. Anyway, so object like this would have its material in these walls, right here and right there. So it's a round object, and this part, the white part inside where I wrote the g of x, that part is hollow. So you can use it for storage. Now this particular shape, right, can be calculated. We can calculate the volume. We can calculate two different volumes. If you use just g of x and the disk method, you can calculate how much stuff this object can store inside, because that would give you the disk method for the volume inside, for the empty space inside, so you know how much stuff you can fit in it. That's important for engineering, right? But another aspect of engineering that is very important is how much material, volume-wise, you are going to use to build this object. Because if you are building some mechanical part, let's say, you don't just order 2 truckloads of raw material arbitrarily, right? Because you need to make 100,000 pieces. You, as engineer, have to calculate very precisely the amount of material, the volume of what you are building. And then you know how many truckloads or train loads of raw material, whether that's plastic or metal or wood or whatever, how many you have to order, right? And then you can have a production and do these kind of things. So now we need to develop a formula that will calculate this. Well, if you remember your area between two curves, this one works the same way. It's far away minus close by. That's what we talked about last time. So now, the volume formula is pi integral a to b, far away, f of x squared, minus close by, g of x squared, in parentheses, the x, and that's your x rotation. It's blue, compadre. V equals pi integral c to d for y limits, and then you have parenthesis f of y squared minus g of y squared dy for the y rotation. And that is known as the washer method. So now, your job is to figure out which function is the one that is far away, which function is the one that's close by, well, process of elimination, right? And then just plug everything in and be done. So, example of this is pretty much the picture that I have up here. So for this picture, f of x is given as the 4th root of x, and the g of x is given as x. Two functions are given to us, and we are supposed to rotate this. Now, here, look. I'm not lying. Upper right corner. It's the same graph that I have, except now you have formulas given, and you're supposed to compute this mess. So, when we learned the area between two curves last time, I told you have to set two equations equal to each other and calculate A and B. Well, that stays the same now. So, we have to set these equal to each other to get A and B, and then plug everything in a formula and go from there. To calculate, so to find A and B, set F equal to G. All right, let's go. 4th root of x equals x. hit each side with the fourth exponent to kill off the root. You get x equals x to the fourth. And now bring everything to the same side. So x to the fourth minus x equal to 0. Factor out x to get x cubed minus 1 equal to 0. Zero product rule sets each one of these to 0. X cubed equal to 1, which gives us that x is 1. And there we have them. A is 0 and B is 1. So finally we can set up our integrals and move on with our life eventually. So pi 0 to 1. Function that is further away is the root function. So 4th root of x squared minus the function that is close by is function x. You have to square that one. It's f squared minus g squared in a formula, dx. And then we integrate. Well, first let's clear the algebra here. 4th root squared, that would just make it a root x, which is x to a half, minus x squared dx. And now we can integrate. Pi integrating, so parenthesis, plus 1. So that's going to be x to the 3 halves divided by 3 halves. Now it's calc 1. X cubed over 3, computed from 0 to 1. So now we're dealing with non-exponential functions, not a cosine, so we can ignore 0. This is pi. The first one over here, when you plug in 1, 1 to the 3 halves is 1. So we have 2/3 minus 1/3, and the whole thing is pi over 3 units cubed. I can't fit units cubed. Try this. Units cubed. There. I mean, I can generate as much paper as I want, but then when I go to export as a PDF and post these notes, it just makes everything very small and difficult to read. So I'm never generating paper to the right. So you gotta look at that ugly thing there. Yes?
So sometimes when I did practice problems, they would have you rotate it from a different point, so not the origin, on that one.
In which case you have to shift the function. So if your axis of rotation is, let's say, at x equals to 2, you would have to shift your entire problem to the left 2 units, which means that every x in your equation will be replaced by x plus 2. So shifting functions from pre-calculus 1 will be necessary at some points, right? So you can shift up or down for x rotations and left and right for y rotations. So if you have to do it, then you just have to carefully modify the function you're dealing with. So let me give you immediately an example of that so we don't have those kind of issues. Say you have square root of x function that is supposed to go from 0 to, let's say, 4. So this is our area that we are considering rotating around the line right here, and this line is now coughing x equals -2. So now the trick is to shift the function 2 units to the right. So your square root of x is no longer going to be square root of x. This is the new situation. So from here, you're going to your new situation where your y-axis is now axis of rotation, and your square root begins at 2, and it's going to end at 6 now, because we shifted to the right because we had to avoid right? The axis, we had to fix the axis of rotation to hit the y-axis. And then, clearly, our function now changed, so it's no longer root x, now it's square root of x. Very good. Excellent. Good.
Wait, why are you shifting it?
Because the axis of rotation was not on the y-axis. Your formulas work only if you rotate on x-axis or on the y-axis, which is why I have that x in a little circle, right? So when your formula is only rotating on x and y-axis and your problem is rotating on a line -2, you have to push your entire problem to the right so that the axis of rotation matches the y-axis. Now that will move the function, and when it moves the function, you just need to adjust the formula for it. And now you just go and plow through regular calculations. Make sense? Happy? Okay. So that's that situation. That's it, guys. That's your disk and washer method 6.3. There will be a whole bunch of examples for you to enjoy the homework, and then if you have any questions, see me during office hours or bring them to class or post in Discord. We can discuss all of these things. Okay, so we'll take a break.